Alright guys, welcome back to part 2. So we had just finished looking at finding probabilities for events using the theoretical approach. And that approach works if we can assume that every single outcome is equally likely. Okay, so for example, flipping a coin or drawing a card from a standard deck of cards. We can assume that you're just as likely to draw one card as you are to draw any other card. Okay, and so we had made it to this subsection here in which we're going to look at calculating probabilities based on relative frequency. Okay, so basically what we're doing here is kind of looking in the past. We're looking at past data and determining how often did that event occur. And interestingly enough, this is actually how they figure out the probabilities associated with rain. Meteorologists, they look at the conditions and they look at past data and they compare the conditions with past data to determine the similar conditions in the past, 60% of the time resulted in rain. And so that's how they come up with a percentage for rainfall. Or at least that's how I remember reading it. It's been several years ago. But so anyway, to kind of motivate this, let's say, for example, that you had a coin in which you weren't as likely to get when you flip it, one side tended to appear more than the other, okay? And it wasn't a 50-50 chance. Each outcome was not equally likely. And so to try and determine the probability of getting, let's say, heads, then you would literally flip the coin several times and see what percentage of times occurred in heads. Okay, so for example, you could flip it 100 times, and if 75 times you got heads, then you could say the probability for me getting heads on this next flip is probably 75%, or at least real close to it. Okay, so let's look at this. A second way to determine probabilities is to approximate the probability of an event by making many observations and counting the number of times that event occurred. So think about flipping the coin and having it come up tails, or heads rather. And this approach is called the relative frequency method. It's also called the empirical method. Okay, and it's very similar. You just define the probability as the number of times the event occurred divided by the total number of observations. Okay, so if I flipped a coin 1,000 times and 600 times it came up heads, then the probability that of flipping a heads would be 600 over 1,000, which would reduce to about 60%. Okay. All right, so let's look at this. It says if you're interested only in the number of heads when tossing two coins, then the possible events are, and we've seen these before, that you could toss two coins and not get any heads, that you could toss two coins and get exactly one head and one tail, or that you could toss two coins and get exactly two heads. They both come up heads. So suppose you repeat a two-coin toss 100 times. So this is what I'm talking about. And these are your results. 0 heads, or in other words, you getting both tails, occurred 22 out of 100 times. Okay, so that's 22 out of 100 is the same as 0.22, which is 22%. And then you got exactly one head and one tail 51 of those times. Okay, so 51 out of 100 is equal to 0.51, or 51%. And then both coins coming up heads occurred 27 times. So 27 out of 100, which is 0.27, which is equal to 27%. Okay, so these would be the relative the probabilities that we obtained through actually performing this experiment 100 times. These are the relative frequencies, okay, for each of these three events. So what we want to do now is compare these probabilities with the theoretical probabilities. And then, furthermore, do we have reason to suspect that the coins are unfair? So what that means is if a coin is unfair, that means both sides are not equally likely to occur. In fact, the coin is weighted in such a way that one side tends to come up more often. Okay, so you can imagine people would use unfair coins for purposes of cheating. But I'm going to say that if these probabilities here are close to the theoretical probabilities, then we don't have any reason to suspect that the coins are unfair. Okay, so the theoretical probabilities, if you come back up here in your notes and look, 0 heads occurred 1 out of 4 times. Okay, so 1/4, and then we got 1 head 2 out of 4 times, so that's the same as a half, and then we got 2 heads 1 out of 4 times. Okay, these are all the outcomes, remember. So from the theoretical lens, it's this outcome divided by the total number of outcomes, which is 4, so 1 out of 4. So I'm going to write these probabilities down here, the theoretical probabilities. Getting 0 heads, it's 1 out of 4, which is the same as 0.25, which is 25%. Getting 1 head and 1 tails, that would occur 2 out of 4 times, which is the same as a half, or 0.50 or 50%. And then 2 heads would occur 1/4 of the time. Okay, so again, 25%. And then those relative frequency probabilities up here were 22, 51, and 27. 22, 51, and 27. Okay, so when I'm looking at these guys, I'm thinking that, well, for one thing, this would be getting just 1 head and 1 tail. It's almost the same in both. And furthermore, this one's a little lower than the theoretical probability, and this one's a little bit higher, but it's not by much. So this would lead me to conclude that the coins are fair. And what actually happens, and this is referred to as the law of large numbers, that if you were to continue flipping 2 coins over and over and over for 1,000 times, and then 10,000 times, and then 1,000,000 times, that these relative frequency probabilities would get closer and closer to these theoretical probabilities. Okay, the more times you flip those 2 coins, the closer your relative frequency approximation is going to be to the actual theoretical probability. Okay. All right. Okay, so 3 approaches to probability. Well, we've talked about 2 of them. The theoretical approach is based on the assumption that all the outcomes are equally likely, and is determined by dividing the number of ways an event can occur by the total number of possible outcomes. So we went over that. And then a relative frequency probability is based on observations or experiments, and it's the relative frequency of the event of interest. So in other words, how many times did the event occur divided by the total number of observations or experiments, or like the total number of flips. Okay, and then there's this last one, and this one is not really mathematical. Subjective probability. It's an estimate on the likelihood of an event occurring or not occurring based on experience or intuition. So subjective probability is something we use all the time. usually based on our experience in life and having lived. We know we can roughly assign probabilities to certain events, okay? Just based on having lived, and basically, if it's based on experience, it's in a way relative frequency, because we're thinking about, well, I have an idea of how many times this occurred in the past, so that gives me an idea about what the probability might be, okay? All right, so what we're going to do in this example is just identify which one of these three approaches to finding the probability is being utilized. So it says, identify the method that resulted in the following statements. I am 100% certain that you'll be happy with this car. Okay. So typically when a probability is associated with someone's gut feeling, like in this case, this is subjective probability. Okay. And this might be based on this person's experience. Maybe the salesman or whoever it is has sold 100 of these cars, and he or she hasn't received a single complaint. So then from that, he or she concludes that, well, the next customer that I sell this car to is pretty likely to be satisfied with the car. Part B here. It says, based on government data, the chance of dying in an automobile accident during a 1-year period is about 1 in 8,000. Okay, this would be relative frequency, because what we're doing here is we're looking back in the past. We're looking at data in the past and assessing the probability that way. And this is typically how it's done with, these insurance companies. Okay, they look at past data to help them determine how likely you are to be involved in an accident, or how likely you are to develop lung cancer or whatever. Okay, so this is relative frequency. And then part C, the probability of rolling a 7 with a 12-sided die is 1 out of 12. Okay, so this is theoretical, because with a 12-sided die, or with any die, you assume that each side is just as likely. Okay. All right. Let's see here. Let's go over this next idea. This is interesting. It says the probability of an event not occurring. Okay, so we've looked at finding or determining the probability that an event will occur. What about determining the probability that an event will not occur? We could be equally as interested in that. So, for example, what's the probability that I never get cancer? Well, that's really broad. What's the probability that I don't develop type 2 diabetes or something like that? So, and interestingly enough, sometimes to determine the probability that an event will happen, it's easier to actually determine the probability that the event will not happen, okay, or vice versa. So let me give you an example. If I wanted to know the probability that it will rain on Saturday, or no, let me rephrase it. If I wanted to know the probability that it will not rain on Saturday, it might be easier for me to determine this by knowing the probability that it will rain. So if the probability that it will rain is 30%, then whatever's left over in probability must be the probability that it will not rain, because one of those two events will occur. Okay, it'll either rain or it will not rain. So if the probability that it does rain is 30%, then 100% minus 30% leaves 70. And that would be the probability that it does not rain. And so that's where this next piece comes from. So if the probability of an event is whatever, then the probability that the event does not occur will be 1 minus the probability that it does occur. Okay? I used this in that example a second ago, except I didn't use 1, I used 100%. Okay? But if you're using decimals for probabilities, then it's going to be 1 minus the probability that event occurs. So think about this. We've talked about, let's just look at this. It says, the probability of a family of 3 having 1 girl and 2 boys is 0.375. Okay. Now we could figure this out by making a chart and listing, kind of like they did for the family of 4 kids, okay, and determining what those probabilities are. So evidently the probability of exactly 1 girl, if that's what we're counting, would be 0.375. What would be the probability of a family of 3 not having 1 girl and 2 boys? Okay, well, it's just going to be 1 minus the probability that they do have 1 girl and 2 boys. Okay, so if 0.375 is the probability that they do have a girl and 2 boys, and the probability that they will not is just the difference there. Okay, so hopefully this makes sense intuitively. You know, if I tell you that you have a 60% chance of passing the exam, then intuitively you know that the other 40% must be the probability that you will not pass the exam. Okay, but this is literally what you're doing. Okay, so, well, I actually know this. I don't need a calculator. This would be 0.625. This would be the probability of not having a girl and 2 boys. Okay, or in other words, the probability of having 0 girls, probability of having 2 girls, or the probability of having all 3 girls, okay, would be this right here. All right. Thinking what we'll do is we'll just go over this multiplication rule, and then we'll call it quits for this video, and then we'll have another short video to finish up this section. Okay. All right, so the multiplication rule of probability. So let's suppose that there's n possible outcomes for one process, and then n possible outcomes for the second process. Okay. So then the total number of possible outcomes for the 2 processes would be m times n. Okay, so let's look at an example. This is called the multiplication rule. So how many possible outcomes are there for the birth of 5 children? Okay, so in this example, we actually have 5 events, or 5 processes, and that being each one is the birth of a child. Okay, so how many possibilities are there for the birth of that first child? Well, that first child can either be a boy or a girl, so there's 2 outcomes there. Okay, times, well, how many outcomes are there for the birth of that second child? Well, there's also 2, because it can be either a boy or a girl, okay? And the probability, or excuse me, the number of possibilities for the birth of that 3rd child is still 2, okay? And so hopefully you see the pattern here. You end up multiplying 2 by itself 5 times, and that is the same as 2 to the 5th power, by the way, which is equal to 32, okay? So if you're planning to have 5 children, there's 32 different outcomes. Think about that family of 4 back up here. If you remember that, the family of 4, there were a total of 16 outcomes. Well, that's because 2 times 2 times 2 times 2 4 times is 16, okay? And that's the way it continues, guys. So the number of ways or the number of outcomes for having 6 children would be the same as 2 to the 6th power, which would be 64. That's why it would be really rare to see a family that had all 6 boys. Basically, you have a 1 out of 64 probability or chance of that happening. So it's a very rare event. That's why you would rarely ever see it. Okay. What about this next example? And we'll stop for now. How many ways can you choose a 3-course meal at a restaurant that offers 3 choices for an appetizer, 5 choices for an entree, and then 2 choices for a dessert? Okay, so because it's a 3-course meal, we can think about this as being made up of 3 different processes. The first process is choosing your appetizer. The second process is choosing your entree, and then the third is choosing your dessert. Okay, so I like to draw a little line. So we're going to be multiplying. So the number of ways that I can choose an appetizer is 3, because there's 3 appetizers available, multiplied by the number of entrees there are, which are 5, and then there's 2 choices for a dessert, so this is going to end up giving us, I believe, 30. So that means that there are 30 different 3-course meals that you could order at this particular restaurant. Okay? So you can imagine if there were more choices. 3 choices for an appetizer is not very many, nor is 5 for an entree or 2 for a dessert at a decent restaurant. At a decent restaurant, these values are going to be much higher. So if you were to multiply all those, you would have a large number of total possible 3-course meals. Okay. All right. Well, we'll stop it right here, guys, and finish up in the next